Hello. In one of my other videos I talk about Thevenin analysis. Today I want to talk about Norton analysis. The basis of Norton analysis is that you've got a current source as opposed to a voltage source. So I've got a current source and a resistance that any circuit or any device that we want to study, we can reduce it to a current source and a resistance. In Thevenin, we reduced complicated circuits down to a single voltage source with a single resistance, and we're going to do the same thing with Norton analysis as well. The rules, quite honestly, are similar. If you remember from Thevenin, first thing we want to do is pick a component to study. Well, unlike my last video, I don't have a circuit ready to go. I was going to build it for you and then talk about some of the things I was doing while I was building it. So let's do that, and I will talk about what a current source requires in a circuit, what a voltage source requires in a circuit, and why we can't necessarily study those parts. Back in Cux, and I want to use a voltage source in this one because we're going to make it a little more complicated than the last video, and I want to use a current source. So this is now a two-source system, and we will go in and we will modify the values here in a little bit. So that gives me two sources. Somewhere along the line there's components, lumped components, that's what I'm looking for. Now I'm going to put a resistor in there, or some resistors in there. As I mentioned the other day, a voltage source has to have a resistor in series, which I really don't like that. Let's go up one more. Escape, highlight, delete. Yeah, it's not too busy. A current source has to have a resistor in series. In parallel. So that's what we're going to do with that. If I mirror that, I can get everything to the right side. There we go. So basically what we're going to do is we're going to boil down any circuit we make. If you do Thevenin, you're going to boil it down to a voltage source with a series resistance, or a current source if you use Norton with a parallel resistance. Now the values obviously will change. To make that a little more clear, this is what we would have in a Thevenin circuit. You're basically boiling everything down to a voltage source there, and then with a resistor in series, or in order to be symmetrical, once we didn't do it this way. Well, I have a little problem drawing my lines today here. That same level. There you go, same square. Beautiful. Looks like I know what I'm doing. Okay. So the end of the day, as a friend of mine used to say, if you do a Thevenin, you come up with a voltage source with a series resistance. You do a Norton analysis at the end of the day, you'll come up with a current source with a parallel resistance. If I was to put a black box over both of those and make them, I could set the values up so that they would have the same characteristics. You would not know whether you were dealing with a voltage source with a series resistor or a current source with a parallel resistor. You just wouldn't know. So anything can be in the black box. So the whole point of Thevenin is to get you to this configuration. The whole point of Norton is to get you to this configuration. It doesn't matter which one. And at the end of the day, they're interchangeable. If you come up with a Thevenin, then you can come up with a Norton. But I want to go through Norton because I want you to see the process. Now what we need is we need a resistor network that we want to study in here. So let's do something like this. And we'll put a resistor there. And we'll go up and rotate it. And what else do we want? Let's let that be enough. So now all we got to do is connect the dots. So now I have a two-source circuit. One with a current source, one with a voltage source. In a lab setting, simulating a current source is not very easy on a trainer. When you get dealing with transistors, you have it. If you ever want to let the circuit software simulate, you got to add a ground, so I always just put one on the bottom. For my purposes, I'm not simulating this software, I'm just using it to build circuits because it's very handy. So let's change our voltage source. We've been using 10 volts, so that's good. If I hit enter, it actually takes it. My resistor here is going to be something other than 50. Let's say 1K. I like that. This one is 2K. Got to pause. Okay, 1K, 2K. This one, 3K. How creative is that? This one, 4K. Ooh. This one, I'm going to go back to 1K. I can't analyze it anyway, but there we go. And then I'm going to hit the enter key, and let's say this is 1 milliamps, probably about right. Let's say it's a 2 milliamp circuit. There we go. Okay. So what I did is I have made a circuit. Now obviously I can't use Norton analysis because this is a Norton thing on R2, and I can't use Norton analysis on R3. Anytime you see a current source in a circuit, you've got to respect the resistor by it, and you can't remove it. Anytime you have a voltage source in a circuit, you've got to have a resistor in series with it. You can't remove it, and it's not good to study Thevenin and Norton because I've done some circuits and it doesn't work out. So learn that the hard way, so I'm trying to help keep you from doing that. All the other circuits, this T here in the middle, R4, 5, and 6, I can study those. So which one do we want to study? Well, the first, if we're going to do Norton analysis, I would suggest what we study is R6. Maybe R5. How about that? R5? Can we do R5? R6. R6, what the heck? We want to pick a resistor to study. Let's pick R6. So going back to this page, in this particular case we're going to do R6. 6. And now we've got our component. For Norton analysis, the second step, unlike Thevenin, is we're going to remove the component and replace with a short circuit or a wire. And calculate the current through the wire. Once we get that calculation and we have that current value, that becomes our Norton current. And that's one of the two things we've got to have. Norton current. That's one of the two things we have to have in order to come up with an equivalent circuit. So now I'm going back. I'm going to take R6 out. I think I can delete it. So I've got two little points here. I can actually go in and draw a line here and say that, and just a little bit here. Let's look at a probe. Current probe. So let's put a current probe in there. And let's rotate it. And we'll that's the problem. We'll rotate it through there. Delete that line, and then what we want to do is highlighting like crazy. Just put a current probe in there. It's not pretty, but it works. I need to know what the current in that ammeter is going to read, basically, is what I'm after. And somehow that got highlighted. Interesting. Okay, there we go. That's what I have to calculate. Now, what I have here is a two-source circuit, so the analysis of it is not as straightforward as it could be, but we can analyze this. Okay, in this circuit I have four unknown currents. I have the current flowing out of my voltage source and into my voltage source. So this current in this C shape here could be unique. I've got the current that I want right there. Then I've got a current flowing here, which interestingly enough has to be the same as the current flowing here. I've got my current source pumping in 2 milliamps, so I know what this current is. That's a known. And then the current through here. So this is one unknown current. This current and this current are the same, but they're unknown. This current is an unknown, and then this current is an unknown. From circuit analysis using Kirchhoff, that means I have to have four equations. I use two current equations. I took the current going into this point is equal to 2 milliamps, and I said it had to be the current that was going through the 4K resistor R5 and the 1K resistor R3. So this current splits into two. So 2 milliamps is this current plus this current. I then took the voltage source, its current, and I knew that the current coming into the voltage source or coming out of the voltage source plus the current coming through this 4K resistor had to equal the current going through that I'm interested in, my Norton current. So that's my second. So I use this node, the current's coming into this node in Kirchhoff's current law, and the current's coming into this node in Kirchhoff's current law. I use the fact that whatever current coming out of this, going around this loop right here, if you remember, ammeters don't have a current drop, so this current's fairly easy to figure out. I've got to drop 10 volts across a 1K and a 2K resistor, so I used a Kirchhoff's voltage loop equation to come up with the third equation. And then for my fourth equation, the current coming into here, the voltage drop across this, and the voltage drop across that have to be the same, because essentially they're in parallel, because if we look at this as being nothing. So these two voltage drops have to in fact be equal to get down to equal potential on this side. That gives me four equations, and I put them in standard matrix form so I can solve them. I'm going to call up my Scilab here, and I'm going to say, okay, Problem Norton equals, and I'm going to do the matrix thing. So my first equation boils down to 0, 0, 1, 1, and 0.02, because I've got to convert it to milliamps. So I want to get rid of the units. So that's my first line. My second line, my second equation is 1 space minus 1 space 0 space 1. I'll show you what my matrix looks like here in a minute, because Scilab's going to show it to me before I solve it. Oops, I don't want the equal 0, I just want a 0. And then 3000 space 0, 0 space 0 space 0 space 10. That would be the voltage loop equation in standard form, put into a matrix. That's going to be another video one day, by the way. 0 space 0 space 0. Close my matrix. See what it looks like. Now, is that what it looks like on my doodle where I did it on paper? Yes, except I got my 2 milliamps incorrect, so I need to up arrow in Scilab. Gives me back my matrix I just typed in, and I actually, instead of 0.02, I need 0.002, because this is 2 milliamps, this is in fact 20 milliamps. So this is what my 4 equations look like in standard form based on what I sort of illustrated. Circuit analysis to that depth is really in part of another class. All I really care about is my Norton current, which will be the answer to this second column. So now I want Scilab to solve it for me. And all I'm going to do is I'm going to reduce row echelon form the matrix. Fancy linear algebra or mathematical term for solve it. So I'm solving essentially 4 simultaneous equations here, and I'm using a shortcut. And what I get is, in my second column, which is my Norton column, 1 I Norton is 0.0037333 amps. That's what I'm after. So I solve my current and I get 0.0037. I Norton Norton equals 0.0037333 amps, which would be 3.73 milliamps, 3.7333 milliamps. Okay, that's the second part. There's some circuit analysis involved. It's complicated. The nice thing about Norton, though, and the same with Thevenin, is you only do this once. Once you get that value, once you get that studied, then you can figure out what your current is. Short circuit, open circuit, different component. You've got that circuit, you're ready to go. The next part of the step is we have to remove the wire and calculate the resistance back through. Just like we did in Thevenin, and calculate the resistance back through. This incidentally becomes our resistance Norton. And resistance Norton, if you're familiar with the Thevenin and the way we did the Thevenin, resistance Norton is going to equal our resistance Thevenin. They are going to be identical. It is the same process. The same assumptions we made for Thevenin we're going to make for Norton. I'm going to virtually short out voltage sources. And I'm going to open current sources for the purpose of calculating the resistor network. So what is that going to look like? Cucks. Okay, so first thing I'm going to do is I'm going to take this out. I've got my gap now. I've got to figure the resistance back through the circuit between this point all the way around this way to this point and all the way around this way to this point. And what's going to happen is this current source I'm going to open up, so I'm going to effectively remove it, giving me no current path, which means my resistance or my network has to go through this resistor. It'll be like this part right here is not even in the circuit. Over here on my voltage source, it's going to be shorted out, so it's like it's not going to be there. So essentially what I've got is a 2K in series with a 1K, and that is going to be in parallel with a 4K in series with a 1K. So series resistance, I add them up. This side's 3K, this side's 5K. So essentially I have a parallel combination of a 3K and a 5K. Again, I'm going to go to Scilab. I don't want to do a lot of hand calculations with fractions, order of operations and all that. So I've got 1 divided by 3,000 plus 1 divided by 5,000. And this is the parallel network. I simplified it from a series standpoint. Before I hit the enter, I'm going to go back and look at cuts, make sure it's right. 5,000, 3,000, we're good to go. Scilab, and now anytime I calculate parallel resistances, it should be less than the lowest. Well, the lowest side is 3,000, so the answer to this should be less than 3,000 ohms. It's 1875. So I have some confidence in my answer. And so my R Norton for this circuit is equal to 1875. And that would be in ohms. Okay? Now it's a matter of doing the completed circuit. So my completed circuit to study the resistor we picked, go back to Cucks and do a new project. So it gives me a second untitled. What it would look like is a current source, a DC current source. And we want to zoom in a little bit. I'll zoom in after the fact. And lump components are always on top, and that gets me. And a resistor in parallel. Let's go down there. And let's tell it to rotate. Beautiful. So, and we will connect the dots. A little line drawing too likes to line draw, that's for sure. There we go. And not the cleanest circuit in the world, but you get the idea. And then if I zoom in a little bit, make it a little bit easier for coming out on the video to see, that is what we look like. Now my current's not right. I just want to change it. There we go. What was it? 3.733 milliamps. This was 1875. That is my equivalent Norton circuit, or my reduced value for studying this. So the gap in my Norton circuit right here is the same gap as you see in this circuit. And that is the advantage of Norton. And I hope this helps. You can go back and add in this resistor. You can study this circuit with a 4K. You can study this circuit for the 2K. You can study this circuit for the 4K. And that is that. Let's see. The rules. I guess rule 4 is construct your circuit. And there are my rules.